Hi everyone, myself Bidyutlata Sahoo, working as an assistant professor in the Department of CSE, Artificial Intelligence and Machine Learning at Institute of Aeronautical Engineering, Hyderabad. This is my 20th video lecture on the course Applied Artificial Intelligence. Today's topic is Game Playing Part 2. In my previous video already I have discussed regarding the introduction to game playing and few more concepts I will discuss in this video. These are the topics to be discussed. First I will discuss two-person games. What is the meaning of two-person game and what strategy it follows, and how to do the status leveling procedure in the game tree. That means how to identify or how to apply the status to the non-leaf nodes if the leaf node status are given to us. Then we'll discuss one of the status leveling procedure with the help of one example. Then one of the classical example of the game tree is name game. So these are the topics today I'm going to discuss. This is the topic learning outcome. After the completion of this topic, students can discuss the role of game playing in artificial intelligence and its significance to develop and evaluate intelligent agents capable of strategic decision making in competitive environments. Okay, all these things already, this two-person game, status leveling procedure, already I have discussed in my previous video, but to explain the name game, again I thought let me discuss in this video so that we can continue to the name game. Okay, so what is a two-person game? So to understand, as the name it implies, two-person game, that means two people will play or two agents will play against each other. So here a few terms we need to remember. So two-person, here one of the person or one of the agent may be the max player, another may be the min player. So max wants a strategy to find a winning state. That means no matter what min does, that means max player always try to win the game, and min player also does the same thing like max player, or at least it tries to prevent the max from winning. And one more important concept here we need to remember, that is full information. Full information means if both the players know the full state of the environment. That means if both the player have the knowledge of the state space completely, then it is called as a full information. And one more important thing, that is partial information, means half knowledge. Only one player will have the half knowledge. That means one player only knows the part of the environment. Partial information about the environment, if it is known to only one player, then it is called as partial information. Some aspect may be hidden from the opponent or from the both the players. Now we can take the example of the card game. While playing the card game, one player knows everything, other player may not have information about the opponent player. So that is a partial information game. Whereas in case of your tic-tac-toe, full information, where both the player will have the complete information about the state space. If we take the example of the carom board or the chess game or the ludo game, then both the player knows both the player will have the complete information about the state space as well as their movements also. Now, let me discuss about the status labeling procedure in game tree. This is one of the very important concept, how to apply the status for non-leaf nodes if the leaf node status are given. Status means in the form of, in artificial intelligence, that in game theory, status of the leaf nodes, that means it can be represented with the help of three symbols. One is win, loss and draw. So win we can write with the help of W, loss we can write with the help of symbol L, and draw we can write using D symbol. Each non-terminal node, which are non-leaf node in the game tree, can be labeled as all the three, win, loss and draw, by using the bottom-up process. That means here in our tree, the leaf node status should be given to us based on the status of the leaf nodes, we have to find out what would be the status of the non-leaf node. That too we have to follow the bottom up process. So that is why it is called as the status leveling procedure in game tree. This is the procedure exactly, the status leveling for non-leaf nodes. Now let me discuss about what is the procedure for max non-leaf node, and another one is min non-leaf node or min non-terminal node. The first one is, if J is a non-terminal max node, then what would be the status of J? So let us suppose first I will write the max node. So for max node, we can write the status can be win, means we are talking about the non-leaf node. It can be win if any of, so what is given the first one, win if any of the J successor is win. That means if suppose there are more number of children, then if any one of the children or child is win, then definitely the successor, which is called as the max non-leaf node, can be denoted as W. Now, second case is, it can be denoted as loss if all the successors are lost. Suppose a node is having 3 children, then it can be denoted as L if all the children are L. Suppose it may be the children may be 2, the children may be child may be 1, or the children may be 3 or 5 or N. So if all the children are L, then only we can write the status of the non-leaf node as L. That to max node. I'm talking about the max node right now. And the third case is draw. Draw, when we can write if any J successor is draw and none is win. Then when we can write D if any one of the child is D. It can be D, but none is win. Means DW combination is not possible. If it is DW, then it can be W. It may be D or it may be DD, or else one more combination we can write D, D and L. Means one of the successor may be D, another successor may be L. In that case also, the non-leaf max node can be denoted as D. So these are the status for non-leaf nodes. So what I have told just now, when we can write W, if any one of the successor is W, then we can write the max non-leaf node as W. If all the successor as L, then we can write the max non-leaf node as L. If any one of the successor is D, in that case we can write as D. Or else, but none is win. W case is not possible. So it may be both the cases may be DD, or one of the cases D, another case of L also. In that case we can write D. So this is all about the max leveling procedure, max non-leaf leveling procedure. Now the second one is if J is a non-terminal min node. Then for this, these are the three procedure. First one is win will take if all the successor are win. That means if all the children are win, then in that case, this is for the min case. Okay, so we can write the status of the min non-leaf node as W if all the successor are W. Second case is loss if any of the J successor is a loss. That means when we can write L if any one of the successor is L. Minimum at least one, then we can write L. And third one is draw if any of the J successor is a draw and none is loss. That means we can write D if any of the successor is D but none is lost. That means it can be W or it can be DD also. If both the successor are D, in that case we can write D. If one of the successor is W, one successor is D, another successor is W, in that case also we can write as D. So this is the procedure how to write or how to assign the status for non-leaf, max and min node. Now we will see one of the example so that the concept can be clear. This is the example. Here two symbols I have taken. One is the square symbol, another one is the circle symbol. Square symbol represents the max player and circle symbol represents the min player. So as it is a 2-player game, both the players will one after the other. So first if we start with the max player, then next level min player. First, this is the first layer, max player. Then next level min will play, next level max will play, next level min will play, then next level max will play, and the last level is min will play. So like this, alternatively both the players will play opponent to each other. Now as per the example, as per the procedure of the assignment of the status leveling procedure, so here we will consider, because all the solutions are given in this, you may not understand, let me tell you. Here the non-leaf, this is one non-leaf node where the status status is given as L. Now these two are non-leaf nodes which are given as status are given as W. Now this is also one of the non-leaf node. This is also one of the sorry. This is one leaf node. I'm talking about only the leaf nodes. Leaf node means where the children are which cannot be further explored. That means it doesn't have any child or children. So then that type of node is called as the leaf nodes. First we have to identify what are the leaf nodes. So this is one of the leaf node whose status is given as L. These two are the this one and this one and this one are the leaf nodes whose status is given as W. This is also, these two are also leaf nodes, status are given as L. This is also one of the leaf nodes, status is given as W. These two are also leaf nodes, status are given as L. And one more leaf node here, it is present at the first layer. I think this is 0th layer. If we consider, then it will be the first layer. So where the status is given as L. So using this status, leaf node status, we have to find out the status of the non-leaf nodes. Means for this one, this one, this one, and this one, these all nodes, wherever I'm putting the tick marks, these are the non-leaf nodes because they are not the leaf nodes. They have the child, so that is why we have to find out the status leveling. Now how to find out the status here. So as per the procedure, we have to follow the bottom-up process. So bottom-up process means which layer is the last layer. This is the last layer as per this diagram. So these two are the bottom layer. But these two nodes are in the mean player. Like we can consider that because mean player is playing at the last level and whose status are given as L. So definitely, if as per the procedure, if you see, when we can write L if any of the successor is lost. So now, but the thing is, here we are not finding the mean layer non-leaf node. We are finding the status of the max node, which is a non-leaf node. Because these two are the mean player, but we are trying to find out the status of the max node, which is a non-leaf node. Then what type of status we can give? As per the procedure, you can see when we can write loss if all the successor are lost. Okay, if all the successor are lost, then we can write as lost. Then definitely as both are lost, so status is your L now. So this is done. As it is done, this is already given. This W is already given. Now one is W, another one is L. Now what is the status of this L? What is the status of this node? Because this node is present in the mean layer. So mean layer status means we'll check what is the status as per this layer. So it would be lost if any of the successor is lost. Now you can see as one of the successor is lost, so definitely it can be a loss. So it is also, we also got it here. Now this node, now we will find out this node. This node is given as L and we got that this node is L. Now what would be the status of this one? Because for max node, if both the successor are lost, definitely it would be lost. Now we got it, this one. Now this is already given. If one of the successor is lost, then what would be the max for the max node? Then it would be lost. As per the procedure, we have every time you follow this procedure and assign the status level. Now check this one. This is W is given and here also W is given. These are the max node, but we are trying to find out the status level for the mean node. So if any one of the successor, for mean node you can check it. If all the successor are win, then only we can consider as win. Now you can see as both the successor here, both the successor are win here. So that is why it is also win. Now this is L and this is win. What would be the status of this one? If any of the successor is W, then for the max node it is considered as W. So for this level is done, this level is done, this level is already there. Anyways, now we will find out this level. Now we okay, already we got it because this is L and this is L. So that is why this is also L. This is L, so it would be L. Now we will find out what is the status of this layer, this mean layer. Now you see the successor here for both the max node. The status is here L and here also L. So what would be the status of this mean node? Definitely it would be L. If both the successor are L, definitely it would be L. Now here it is W, definitely the successor, the parent node, the non-leaf node which is present in the mean layer, it would be W. Now this is already L is given. Now we can find out what is the status of the root node which is in the max layer. So if any one of the successor is W, as it is W, so definitely the status would be W. So like this we can find out all the status of the non-leaf nodes if the status of the leaf nodes are given to us. I hope you might have understood. For like, it is a bit complicated, but it is very easy also if you remember the rules or the procedure or the strategy to assign the status of the non-leaf nodes based upon the status of the leaf nodes. So this is the same thing here I have mentioned. Here the max node, which is represented for this particular diagram, the max node is represented as the square symbol, and which tries to maximize the chances of winning, whereas the mean node, which is represented as a circle, the player tries to maximize the max player's chances of winning. And two levels on the edge we have mentioned here in this diagram. You might have observed here everywhere +1 -1 is written. Especially +1 means it is a good move, -1 means it is a loss, whether irrespective of any layer, whether it is a max layer or mean layer. If it is W, it is written as +1. If it is L, it is written as -1. Okay, and leaf nodes, which is marked as W and L. Here we have not used T. Even if the question is given with the LWD also, the same procedure we have to follow as I have shown before. Now, one of the classical example in game theory is the name game. The name game, it is a mathematical strategy game where two players take turns removing the objects from one or more piles. The player who takes the last object wins the game or lost the game. That depends upon the type of game. Actually, there are two types of game. One is the normal name game, another one is misery name game. So, as per the problem statement of name game, the player who takes the last object from the pile of object, maybe he or she may be the win the game if it is a normal game. But in case of the misery game, the person who takes the last object will be the loser. So that is what two versions of name games are there. One is the person. Definitely we have to check who is taking the last object from the pile of objects. So it is a classical example of two-player perfect information game with a deterministic outcome. First of all, it is a two-player game which follows the minimax strategy. One is max player, another one is the min player. Perfect information game means all the information regarding the state space of the environment is known to both the players and with a deterministic outcome. Deterministic outcome means what? If every output of every action can be determined in advance, then it is called as deterministic outcome. So that is why it is a two-player perfect information game with a deterministic outcome, meaning one player always has a winning strategy if they play optimally. Normally, especially we know that in minimax game, max player always tries to win the game. So let me tell you what are the rules for the classical name game problem. These are the rules here. It is visible on the screen. The game starts with multiple piles of objects. Each player on their turn must remove at least one object from a single pile. That means if we have 10 objects, suppose two players are playing, first player will have the chance either it can remove one or two objects from the pile of objects. That means if the first player removes one object, then how many will be remain? How many? It would be 9. If out of 10, if it removes two objects, then how many will be remaining? 8. So like this, now the first player turn is over. Next player has to play in the next level. Like the same process will be followed until all the objects are not finished from the pile of objects. That is what the name game says. So here the first step is the game starts with multiple piles of objects. Each player on their turn must remove at least one object from the single pile. The game continues until no objects remain. And the player who removes the last object, either it will be considered as winner or loser. When the person is considered as winner if it is a normal win game, a normal name game, and when it will be considered as loser if it is a misery name game. So there are two versions of name games are there. Okay. Now, this is very important. How to assign this status W or L in this name game? We need to remember these two formulas. A player is marked as L, that means losing, if they are forced into loss. I mean, no further movement. Okay, and second one is a player is marked as W if they can force the opponent to lose. Okay, so I will show you, I will prove these two lines with the help of example so that the concept will be clear. A player is marked as loser if they are forced into loss, and a player is marked as W if they can force the opponent to lose. Okay, normally in two-player game, minimax strategy, always max tries to win the game, and the same thing mean player also tries to win the game. At least it tries to prevent the max advantage. Okay, so using that concept, we will apply this L and W to the non-leaf nodes. Now you can see the nim game tree here with the solution it is given. Anyways, I will explain. Let me tell you about this tree here. So this tree looks like the previous game tree with like one is the min, like two players are there. One is max player, another one is min player. Both the players alternatively play against to each other. Okay, if the max player starts the game, then min player will be the next player, then max, then here the max player is playing the first, taking the first option, then min player, then in this layer who will play, max will play, in this player min will play, and in this layer max will play, and the last layer min will play. Okay, anyways, for better configure, better recognition, we have taken two types of symbol. One is the square symbol, which is represented for which represents the max player, and the circle symbol, which represents the min player. Now let me erase everything so that because the if I write everywhere it would be too complicated. Let me introduce regarding this game, then I will come back to the problem. So here the image represents a game tree for a nim game where the squares represents the max player node whose goal is to maximize their advantage. Just now I have discussed, always the max player will try to win the game, or else always the goal is of the max player is to maximize their advantage. And the circle symbol represent the min player node who try to minimize the max advantage. And each node contains a number indicating that the number of objects remaining. Okay, what is the meaning of the third statement? Each node is containing some number indicating that the number of objects remaining. Now you can see at the first layer 5 objects are there, and that node is present in the max player. So max player will start the game here. So as per the procedure for the nim game problems, as per the problem statement of nim game, the max player, whoever will start the game, doesn't matter, but it can take or it can remove one or two objects at a time, minimum one object, or one or two or more than two also it can remove. Okay, so if the first player remove one object from here, how many will remain? 4. If it removes 2 objects from 5, then how many will remain? 3. So like this the process will continue until the leaf node. I will explain then. Then the last point is the game follows a minimax strategy evaluating the optimal moves for both the players. And the max player, which is nothing but the square node, tries to maximize their chances of winning. The min player circle node tries to minimize the max advantage, and the values assigned to all the nodes represents with the help of two symbols. One is +1 and -1. +1 means winning and -1 means losing the positions. And the minimax strategy, here we are following one of the strategy that is nothing but the minimax algorithm, which is used to determine the best move. The max tries to get a position with a value +1, which is win, and min tries to force max into a losing position, that is -1, and the evaluation propagates upwards and max choosing the move that maximizes its advantage. Okay, let me go back to the problem so that we can understand. Now, here total 5 objects are there. The pile of objects is nothing but total objects. We have 5, and the first player is max player. So, as per the problem statement of nim game, the max player either it can take 1 or 2 objects at a time. So, if it takes left side, if it takes 1 object, then how many will remain? 4. If it takes 2 objects, then it will remain 3. Remaining will be 3. Now who will play for the next player? Next player is mean player. So the same procedure will be followed for the mean player also. Mean player can also take 1 or 2 objects at a time. So if it takes 1 object from 4, then 3 will be remaining, and if it takes 2 objects from 4, 2 will be remaining. Now same thing from 3 also, because here 3 objects are remaining. So remaining 3 objects from 3, if it takes 1, then 2 will remain, and if it takes 2, 1 will remain. Okay. Now whose turn here? Turn is max player. Now max player, the same procedure will be followed. Max can take either 1 or 2 objects at a time. If it takes 1, 3 minus 1, it would be 2. If it takes 2 objects, then 2 minus 2, it will be 0. Now from here, 2 objects, total remaining objects are 2. So 2 minus 1, it would be 1, and 2 minus 2, it would be 0. Now from this object, 2 are remaining. So 2 minus 1, it will be 1. 2 minus 2, it will be 0. Same thing, only 1 object is there. So 2 objects cannot be taken. So 1 minus 1, it would be 0. Now wherever you are finding 0 means their game is completed. Now whose turn here in this layer? Still some numbers are visible apart from 0, because here 2 is there, here 1 is there, here 1 is also there, here 1. So next turn will be for mean player. So mean player will play. Now same procedure will be followed for mean player. So it can take 1 or 2 objects at a time. If it takes 1 object from 2, remaining will be 1. If it takes 2 objects from here, remaining will be 0. Here only 1 object is remaining, so it can take only 1, so it would be 0. Here only 1 object is remaining, it can take only 1, remaining will be 0. Here already 0, no need to touch, because game is completed over here for this player. And here only 1 object is remaining, so if it takes 1, remaining will be 0. Now this layer is completed. Still in this layer who will play next turn is max. So we have to play, both the max and min player will play against to each other until no object is found in the pile of objects. Now still one more object is remaining. So for this layer, max player will play and take 1 object, and remaining will be 0. Now, okay, let me remove this 1 or 2 so that you will not get confused. In between some numbers I have written. Okay, this one. Okay. Now, how we can assign the status of this status, either L or W. So as per the strategy, as I told here, a player is marked as L if they are forced into loss. I mean, no further movement. You can observe over here. First we will check for the leaf nodes. Okay. Now for this mean player, we have written as L. For this mean player, we have written as L. For this mean player, we have written as L. Even for this mean player, because game is already completed. Wherever 0 is there, I am touching to those nodes, because circle represents the mean player. So it is represented as L. It is also represented as L. It is represented as L, and it is represented as L. Well, how we are getting as L? Here, as per the problem statement of name game, if the game starts with the max player and max is taking the last object, okay, here max is starting the object, and here max is this one, especially this one, max is starting the game, here max is taking the last object. Definitely who will be the loser? Mean will be the loser. That is what it is given. A player is marked as L if they are forced into loss. Who is forcing? Max player is forcing to loss for the mean players. That means if it is max player, if it is the mean player is loser, no further movement from that side. Now another case, now you can see. So this one we have marked as L, this one also we have marked as L, this one also we have marked as L, and this one also we have marked as L. These 4 leaf nodes, that to mean nodes, we have marked as L. Now you can see another 4 are there where we have marked as W. This one, okay, this W and this W, this W, and one more. These 4 are we have marked as W. Why? Because you see, a player is marked as W if they can force the opponent to loss. That means what? Here max is starting the game, and who is taking the last object to make the max player as win? Because mean layer is taking the last object here. So 2 minus 2, we are getting over here 0. So max is starting the game and mean is taking the last object. That is why forcing, that is why the it is forced, sorry, a player is marked as W if they can force the opponent to lose. Who is here a loser here? So definitely, because mean player is taking the last object, that is why it is considered as loss. So that is why the max player will be considered as W. So two things here we need to remember how to assign W and L. If the max player is starting the game and max player is taking the last object, then mean player will be the loser. Second case, if max is starting the game and mean player is taking the last object here, mean player is taking the last object here, mean player is taking the last object here, also mean player is taking the last object, in that case max will be the winner. So using this, if we find all these leaf nodes W and L, I hope you can assign rest all W and L for all the non-leaf nodes by using the status labeling procedure what I have just discussed before. And very simple, this plus 1 and minus 1 we have allocated, like wherever there is a win we can write plus 1, if it is a loss we can write minus 1. And why we are writing plus 1 and minus 1, let me tell you over here only one example, because suppose I'll take the example of here, this is plus 1 and this is minus 1, because this node is denoted as W and this is denoted as L. So plus 1 minus 1. So what would be the value for this one? Definitely plus 1. How it could be plus 1? Because this layer is the max player. So how to find out? So what is the max between plus 1 and minus 1? Definitely it would be plus 1. Same thing here, this node is L and it is denoted as minus 1. So what would be the value for this node? It would be minus 1, because for max layer, max of only one value, that definitely it would be minus 1. So like this, all this value we can write plus 1 and minus 1 depending upon W and L. I hope you might have understood this problem, and in this problem we are finding two appropriate solution. One solution is from 5, 4, 3, then 2, then 1. This is one solution. Another solution 5, 4, 3, 1 and 0. These two are correct solutions in this problem. How we are finding the solution? Up to the wherever we find the solution is like there is no object in the pile or in the storage or in the pile of objects, then we can say that is our solution. But still 2-3 solutions are also available, but those solutions we don't consider. One more, these two are correct solution. One is 5, 4, 3, then 2, then 0. This one. Another one is from 5, then 4, then 3, then 1 and then 0. These two solutions which I have highlighted. These two are the correct solutions. Two more solutions are there. If we consider here 5, 4, 2, then 1, 0. This is also one solution. Another one is 5, 3, then 2, 1, 0. Now you can observe in these two solutions, here 2, 1, 0 and 2, 1, 0 are common in both the solutions. That is why as like after one level it is both the solutions looks like redundant, so we don't consider those two parts are the good solutions. So we used to consider these are the correct solutions. I hope you might have understood this name game properly. So here I have mentioned the solution. The two winning paths shown in the figure 54320 and 54310 are likely chosen because they are clearly demonstrate the strategy needed for Max to win, because here Max started the game and Max won the game, and other winning paths might exist like just now I have shown, but are not shown for simplicity because they are redundant, means they looks like equal. So this is all about this game theory introduction. Especially I discussed how to apply the status label for the non-leaf nodes if the leaf node status are given, and the name game tree. For the preparation of this video, I have followed the stochastic book for artificial intelligence, as well as this website which is given on the screen. Next class I will discuss the bounded look ahead strategy and the use of evaluation functions, followed by the Minimax problem as well as the Alpha-Beta Pruning. So till then, thank you. Take care. Bye bye.
Like, share and subscribe. hit the bell icon for more updates.